All right, we're going to take a peek at our homework from the weekend, worksheet number 7. We're going to do question 1A, B, and D. We're going to do B first, though. Question B says, find the net force on the second charge. We got 3 charges that are described up here in the stem of the question. So let's draw that out and then find the net force on that second charge. It says we have first charge, it's 5.00 times 10 to the negative 5 coulombs. We call that charge number 1. It's positive 5 times 10 to the negative 5 coulombs. We got a second one that is also 5 times 10 to the minus 5. And it's 2.5 centimeters to the right of the first one, or 0.025 meters to the right of the first one. Then the third one over here to the right of the second charge, it's 0.02 meters to the right of the second charge, or 2 centimeters to the right of the second charge. And we know its charge is negative 2.50 times 10 to the minus 5 coulombs. Remember we said when we plug numbers into equations, we don't plug the sign of a charge in ever, but we're drawing a diagram, we do that. We want to do that when we're drawing a picture to help us determine whether forces are attractive or repulsive, and therefore which direction the forces end up acting, left or right. Find the net force on the second charge. If we pretend that number 3 doesn't exist for a second, then which way does number 1 act on number 2? There's a force between them, right? They're both charged. They're going to push each other away or pull each other towards each other. What do we got between 1 and 2? Again, pretending number 3 doesn't even exist right now. Is it attraction or repulsion, Ollie?
I believe that's going to be repulsion.
Yeah. Yeah, good. It's repulsion because they're like charges, both positive. If they were both negative, we'd get exactly the same thing happening there. Now, if number 1 and 2 repel each other, number 1 is going to be pushed to the left, and number 2 is going to be pushed to the right. Which one do we care about? Yep.
The one that's being attracted.
The one that's, this one you mean?
Yeah.
Okay, the one that's being pushed to the right? Yeah, that's the one we care about, the force of 1 on 2, because we're trying to find the net force on number 2. Now, in question A, we were looking to find the net force on number 1. We would have cared about the force on number 1 there, F21 in that case. All right, now pretend number 2 doesn't, hold on. Yeah, now pretend number 1 doesn't exist. Pretend number 1 doesn't exist. Did number 2 and 3 attract each other, or do they repel each other? They're going to attract each other, and how do you know that? Yeah, opposite charges, positive and negative, are going to attract each other. So number 2 is pulled towards number 3, and number 3 is pulled towards number 2. Which one do I care about, the one that's to the right or the one that's to the left there? The first one or the second one here? Yeah, I don't care about the second one at all, right? It's the first one that I care about. We're going to call this F32 because we're trying to find the force on number 2, on the middle one. If I was trying to find the force on number 3, which I am in question C, then I would have ignored this one and paid attention only to the one that was acting on number 3, the other one that was acting to the left. All right, got to get both the values of these forces now. F12 is KQ1, Q2 over R squared. F32 is K Q2 Q3 over R squared. Now, I'm going to assume that you can plug the numbers in there and calculate those values. If you're having trouble getting the correct values, then let me know and I can go through the work here. But I'm going to trust right now that you can do that. When I do F12, I get a value of 3.596 times 10 to the 4 newtons. When I do F32, I get a value of 2.8094 times 10 to the 4 newtons. Now, once we have both of those forces, what are we going to do? Yep. Yeah, we're gonna add them together. F net is equal to the sum of the forces. It's going to be F12 plus F32. Now, we haven't plugged in signs of the charges into the equations. We haven't done that because we don't want a negative value of force here. For us, a negative value of force has got to mean direction, not attraction or repulsion. I'm going to determine what direction it is, right or left, by the diagram. I can see that both of my forces are to the right in this picture, so I'm going to make them both positive. 3.596 times 10 to the 4 plus 2.8094 times 10 to the 4. And when I add those up, both positive values, I end up getting 6.41 times 10 to the 4 newtons. And it's a positive value, which means the net force is to the right, which makes sense, right? If you have two forces acting to the right, then the net force, or the total force, has got to be to the right as well. Okay, let's take a look at question A now. We want to look at A and D, but the two of those kind of go together, right? Once again, we have the same three charges. Here's the first one, second one, third one. My distances are 0.025 meters, 0.02 meters. Charge number 1, 5 times 10 to the minus 5, 5 times 10 to the minus 5, and a negative 2.5 times 10 to the minus 5. There we go. There's my, call this a situational diagram, when we're just drawing a diagram that describes kind of what's going on, but specifically showing the forces is a free body diagram. So let's show those now. The forces on the first charge. Number 1 and 2, do they attract or repel each other? They're going to repel each other because they're both like charges, right? That means number 1 is going to be pushed this way away from number 2, and number 2 is going to be pushed this way away from number 1. Which one do I care about, the first one or the second one? The first one. The second one is, I mean, it's a valid force on number 2, but that was only relevant to question B. So let's forget about that one, and let's look at this one, the force of 2 on 1. Now, we calculated the force of 1 on 2 already. It's going to be the same value, right? F21 has a value of 3.596 times 10 to the 4 newtons. Now, what about 3 and 1? Do they attract or repel each other? Or do they attract or repel each other, 3 and 1? Yeah, they attract each other because they're opposite charges. That means 1 is going to be pulled towards number 3, and 3 is going to be pulled towards number 1. Which one do I care about, the first one or the second one? First one or the second one? The first one, yeah. We don't care at all about the second one because although it's a force that's legitimately acting on number 3, we're not trying to find the force on question or on charge 3. That would be question C, right? Now, we don't know what the value of F31 is. We're going to have to calculate that one. KQ1 Q3 over R squared. That's going to be 8.99 times 10 to the 9 times Q1, 5 times 10 to the minus 5 times Q3, 2.5 times 10 to the minus 5, dropping the sign of the charge, divided by, what would R be? What would R be? 0.02, 0.025, what is it? Fraser? Good, 0.045. A lot of people look at this and say, like, how does number 3 affect number 1 when number 2 is in between them? It does. Okay, I think I used this analogy here the other day on Friday when we were talking about this. Okay, if Brendan has a rope attached to him and I'm pulling on that rope like this with a force of 100 newtons, and then Cale comes over, stands in between us, pulls on Brendan with another rope with a force of 50 newtons, well, both ropes matter, right? Just because Cale's standing in the middle doesn't mean the force that I'm applying on Brendan doesn't apply anymore. It does, of course. I apply a force of 100, Cale applies a force of 50 in the same direction. The net force on Brendan would be 150. Well, the same deal here. Just because number 2 is in the middle, like Cale was in the middle there, doesn't make any difference. Okay, we have to figure out the force of 2 on 1, but we also have to figure out the force of 3 on 1 as if 2 wasn't there. Peter? We do this math here, we get a value of F31 of 5.549 times 10 to the 3 newtons. Now we're going to add these up using F net is equal to the sum of the forces, F21 plus F31. And remember, we didn't pay any attention to the negative signs in the charges, so we got both positive forces. But since one of them is to the left, we're going to make it a negative value. And since one of them is to the right, we'll make that a positive value. I do the math there, works out to be 3.04, negative 3.04 times 10 to the 4 newtons. Listen, it's okay to have a negative thing in there now. Okay, that's showing us direction, not a type of charge. We just don't want to plug the negative in for the type of charge. Okay, finally, we're looking at question D here, which says, if the first charge is a mass of this value, what's its initial acceleration? Listen, whenever you're trying to find acceleration in physics 30, like literally 99% of the time, then I want you to use F equals m times a. But of course, to do that, you need to find the force. Sometimes that force will be a gravitational force. Sometimes it'll be a magnetic force. Sometimes it'll be an electric force. It doesn't matter what kind of force it is. If you want to find an acceleration, get the force, and then divide it by the mass. We just got the force. Okay, we found that it was 3.04 times 10 to the 4. And we're just given the mass 7.50 times 10 to the negative 2 kilograms. And we do the math on that, and we get a value of 4.05 times 10 to the 5 meters per second squared. Which, honestly, if I was, should be negative actually, so it's to the left. If I was predicting what the value would be before I calculated it, I wouldn't necessarily predict 10 to the 5, but I'd predict big. Right, I predict a big value. A big value because mass is small. Usually, big accelerations go with small masses. And that's why when if you ever go camping with your big, 28-foot travel trailer behind you, towing behind you in the truck, you know that you can't accelerate the truck nearly as quickly with your travel trailer attached. Right, or any kind of trailer attached as you can without it attached, right? Because the mass is so much greater, the acceleration goes down. All right, I would like everybody to have a quick look at question number 2 and see if they can, at the very least, set that up, and then we'll take a look at it as a group. This is a challenging question, all right? This is more challenging than you're likely to see on a diploma exam. In fact, I'd be shocked if you saw something this mathematically challenging on a diploma exam. But it's good exercise, right? Just like sometimes when you're practicing for a sport, practice is sometimes harder than the game. Okay, this is practice being harder than the game. Let's see what we can do with it, because it makes game day easier if you end up being able to do this. All right, let's have a look here now. This question number 2 says, situation described above, first and third spheres remain at their original positions. Let's draw those ones because their positions haven't changed. Here's 1 and 3. 1 is negative 2.5 times 10 to the negative 9 coulombs. 3 is negative 1.0 times 10 to the negative 9 coulombs. And it looks like they're 3.5 centimeters apart, or we'll make them 0.0350 meters apart. Okay, 1 and 3 are that far apart because normally number 2 would be 1.5 centimeters to the right of number 1, and number 3 would be 2 centimeters to the right of number 2. So 1 and 3 have to be that far apart. Now, we're putting number 2 somewhere, not in the middle. That's not going to balance the forces because the charges aren't the same, but we're going to put it somewhere in between charges 1 and 3. Don't know where exactly. I'm going to draw it in the middle, but I know it's not going to be exactly in the middle. That doesn't really matter. Its value, by the way, is positive 1.5 times 10 to the negative 9 coulombs. We know that the net force has to be 0, so we know that the forces that are acting on this must balance each other out. Let's just make sure we got the directions right here. Number 1 pulls number 2 this way. We'll call that F12 because it's an attractive force. Number 3 pulls number 2 this way because, once again, it's an attractive force. Force 1, 2 is opposite to the direction of force 3, 2. That's good. If we want the net force to be 0, we have to have 2 forces balancing each other. What else do we know about F12 and F32 if they are balancing each other? If the net force is 0, Rosie? Good. They have to be equal in magnitude to each other. So I'm going to say the force of 1 on 2, the magnitude of it, is equal to the magnitude of the force of 3 on 2. The direction is opposite, right? I'm just putting the absolute value signs around them so they don't have to worry about the negative sign in there. All right, F12 is K Q1 Q2 over R squared. F32 is K Q2 Q3 over R squared, right? Well, what's the value of R? 0.035? Ollie, what's the value of R? Well, we don't know where it is. Was it? Yeah, that's what we're actually looking for. We're going to say R is the distance between 1 and 2. Well, if R is the distance between 1 and 2, then it all works over here. But what about over here? What do I put for the value of the distance that separates them there? Kevin? Good. Okay, if this distance is R and this is 0.035, then this distance between 3 and 2 must be 0.035 minus R. Remember, just like with variable value changing, we talk about a variable, we represent it by a symbol, but that's not really the variable. The variable is, in this case, the distance that we're representing now by 0.035 minus R. Okay, this is not looking pretty here. But there is good news. And that is that I can cancel a couple things here. K cancels because it appears in both. Q2 cancels because it appears in both. I'm left with Q1 over R squared equals Q3 over 0.035 minus R squared. Well, we know the value of Q1 and Q3. That's easy. So let's plug those in. Q1 is 2.5 times 10 to the negative 9. Drop in the sign of the charge, as we always do. Q3 is 1.0 times 10 to the minus 9. Okay. Now we have one equation with one unknown. How do we solve for R, though? Ouch. Ouch. How do we solve for R? Ethan, is your hand up there? Square everything? Okay, let's try that. Or square root everything.
Well, you could do that. Just take the square into the 0.035.
Oh, I see. So foil it, basically. Okay. Yeah, you could do that. I don't want to get into foiling it, though, because there is an easier way to do it, actually. But no, you absolutely could. Okay, and then you could combine terms, and you could make it work that way. More work, though. Ethan's saying, guys, 0.035 minus R squared is the same as 0.035 minus R times 0.035 minus R, and then you use FOIL, right? First, outside, inside, last, to get a quadratic there. What are we going to do there, Ollie?
What I was thinking, because I don't know, because I'm still on the loop. And I see R squared, but you see all the other three have nothing else.
Yeah.
So
yeah.
For the R.
Yeah.
So I'll go across multiplying and dividing.
Okay. Okay. No, let's go there. Yeah, let's cross multiply. I like that, actually.
See, the bad thing is.
Oh, there's a bad thing?
Well, there's always going to be a bad thing.
Okay, good and the bad.
Yeah. Okay, so the bad thing is there's R square.
Yeah.
There's R and then bracket square. So
yeah.
Can we cancel out the square?
No. No. Not directly, but you're on the right track here. Okay, I'm going to do what you suggested first, and then we'll see if. No, it's not wrong.
It's not wrong.
No, absolutely not. We'll see if anybody else can figure out what to do next. So I'm going to take the 0.035 minus R up by multiplying. Right, took it up to the other side by multiplying. And then I'm going to take the R squared up by multiplying. That goes up there. Okay, so we've simplified it a little bit here, right? Now what? Yeah, now let's square root the whole thing. I can do that, right? I can do whatever I want as long as I do it to every term. Now, this is going to really simplify things big time. Although the math's still a little bit tricky here. We're going to say the square root of 2.5 times 10 to the minus 9 is 5 times 10 to the minus 5 times 0.035 minus r. Where did that square go? Well, that's gone because I square rooted it. Sorry, I got to square root 1 times 10 to the minus 9. And I get 3.162 times 10 to the minus 5 times r. Look at this. Still a little bit ugly, but it's looking better every step along the way. Now what I want to do is distribute this 5 times 10 to the minus 5. Okay, let's take it inside there. So 5 times 10 to the minus 5 times 0.035 it gives me 1.75 times 10 to the minus 6 times, or subtract 5 times 10 to the minus 5 r. See what I've done there, guys? I've taken the 5 times 10 to the minus 5 and multiplied it by both terms inside the brackets. That equals 3.162 times 10 to the minus 5 r. Now, here's a question for you. Kale, if I have one apple and I add 2 apples to it, what do I have? 3 apples, right? So if I said 1r plus 2r, that would be equal to 3r. Or I could say 3.162 times 10 to the minus 5r plus 5 times 10 to the minus 5r gives me, on the right-hand side, when I take that over, 8.162 times 10 to the minus 5 r. Combining my r's here. Oh, look at this. And now it looks actually pretty straightforward. I'm going to say 1.75 times 10 to the minus 6 divided by 8.162 times 10 to the minus 5 gives me a value of r of 0.0214 meters. So there we go. R is 21.4 centimeters, or sorry, 2.14 centimeters. Okay, we know the value of r. And now if we want to find the other value, between 2 and 3, all we're going to do is say 0.035 minus 0.0214. Look at this. 2.14 times 10 to the minus 2 meters to the right of the first charge. Here's another question that I'd like to take a look at. Listen, this one is pretty similar to what we've just done. Not the exact question we've just done, but the topic that we've just done, 3 charges in a row, find the net force on one of the charges. What's the difference between this one and the other ones? Well, this one, we have 3 charges like this. Charge 1, charge 2, charge 3. Charge 1 is 2.1 times 10 to the minus 6. It's actually negative. Charge 2 is positive 1.50 times 10 to the negative 6. And charge 3 is 1.80 times 10 to the minus 6 coulombs. My distances, what do we got here? 0.02 meters. And between 2 and 3, it's 0.03 meters. You know, I feel pretty confident that you guys, some of you guys at least, could actually solve this question without me helping you. But we'll do it as a group anyways. Okay, let's have a look. What's the first thing we're going to do in this question, huh? Ollie?
We're gonna look at it.
Okay, after we look at it?
We're gonna see what they track.
Yeah, we're going to look at the forces, right? We're going to draw the forces on this diagram. We're looking for the net force on number 2. So I want to draw the force of 1 on 2 and the force of 3 on 2. 1 and 2 attract each other because they're opposite charges. That means 2 is going to be pulled towards number 1. Now, 1's also going to be pulled towards number 2, but I don't really care about that since that's not the question. F12 is the force of 1 on 2, and it's pulled to the left. What about 3, 2? These are like charges, both positive. So that means 3 is going to push 2 upwards like this. 3 is going to be pushed downwards. 2 is going to be pushed upwards, but I don't really care what happens to number 3. Now, what next? Rosie? Yeah, I need both of those forces, right? I need the value of F12, and I need the value of F32. KQ1, Q2 over R squared. And I'm going to say F32 is KQ2, Q3 over R squared. Does anybody have the value of F12 here? 79625 newtons. Everybody agree with that? Okay, thank you. And what's the value of F32? Don't forget to square the distance, right? Yeah. 26.97 newtons. Agree? Okay, good. Now what? If we want to find the sum of the forces, then we have to add them together, right? But how do we add these two vectors together? Yeah, let's make a triangle. A vector diagram triangle, right? And vector diagrams, you remember, have to be drawn front to back. We can draw F12. That's 70.79625. F32, 26.97. That's not drawn to a very good scale, but that's okay, I guess. Want to find the resultant vector there and the angle because force has a direction. We're going to do the Pythagorean theorem. What do you end up getting there? 75.76 newtons, which is going to round to 3 digits, 75.8 newtons. And theta is going to be the inverse tan of opposite over adjacent. What do you get for that one, Fraser? 69 degrees, so mine's going to be 21 degrees. 20.9. This is going to be 20.9 degrees. We're not going to bother saying north of east here because our frame of reference is not a north, south, east, west frame of reference. We'll just label the diagram as 20.9 degrees. Now, Fraser did it the other way. You would have gotten 69.1 degrees, okay, which is absolutely fine if you had it drawn it like this. Right? Listen, we can do that, right? We can do that. All right, now that you seem to have figured that one out all by yourselves, let's see what we can do with the questions on 534.